Okay, let's dive right into this. I want you to picture this exact scenario. You are sitting in the exam hall, the clock is ticking down, the silence is kind of deafening, right? And you turn to the final pages of your Cambridge mathematics paper. Maybe it's 0580, maybe it's the core additional mathematics 0606, or even the 4024, 4037, and 4040 variants. And there it is, the absolute ultimate wasteland of lost marks. A massive, intimidating, multi-part question focused entirely on connected rates of change, small increments, and approximations. For so many students, this section right here is an absolute nightmare. It's like a chaotic fury road where A-star dreams literally just go to fade away. But listen to me, it absolutely doesn't have to be that way. Today, we are transforming this exact source material, the official, actual Cambridge Principal Examiner reports and their theoretical frameworks, into a visual, highly structured masterclass explainer. We're going to completely decode the examiner's mindset, we'll break down the complex calculus, and I am going to give you the ultimate strategy to navigate this tricky terrain and claim your grade treasure. So get ready, because we are taking all of that exam anxiety and turning it into pure, unfiltered analytical power. The reality of this specific topic is pretty stark, guys. Straight from the senior examiner report, they literally state, this is one of the most misunderstood areas in additional mathematics. Let's look at exactly why that happens by introducing two typical candidates. First up, we have Alex. Now, Alex is the classic over-preparer. Alex has memorized literally every single formula in the textbook. But when faced with a connected rates problem, Alex just overloads the page with raw mathematical facts. We're talking calculating random derivatives, writing down everything they know, but with zero structured analysis or logical progression. It's basically a shotgun approach, just desperately hoping something hits the mark and catches the examiner's eye. And then, on the other end of the spectrum, we have Sam. Sam actually really understands the math, but Sam always rushes. Because of that speed, Sam misses the specific command word requirements, completely ignores the physical context of the word problem, and forgets to verify if the final answer actually makes any sense in the real world. Both Alex and Sam bleed massive amounts of marks here. And the crazy thing? It's not because they're bad at calculus. It's because their fundamental approach to executing the answer is flawed. And that is exactly what we are going to fix today.
All right, really quickly, here is our roadmap for today's explainer. The challenge, cognitive domains, the 5-step methodology, our interactive workshop, and finally, the final blueprint. Section 1. The challenge. Let's clearly define this wasteland so we know exactly what we're up against.
Getting the core definition right is absolutely crucial here. When we talk about connected rates of change in small increments, what are we actually doing? We are applying differentiation to logically relate variables that change over time or by minute tiny amounts. Think about the chain rule for a second. dy dt equals dy dx multiplied by dx dt. Said out loud, it sounds relatively simple, right? Just a bit of algebra, but the principal examiner report comes with a massive flashing red warning right here. Candidates consistently confuse key terminology. You literally cannot just throw dy dx onto the exam page and expect full marks. The examiners explicitly state that you must define your terms before using them in these extended responses. If you are using v for volume and r for radius, you have to clearly state that dv dt is the rate of change of volume with respect to time. Why? Because defining your terms essentially builds the foundation of a structurally sound mathematical argument. If you don't define the building blocks, the whole house collapses under the examiner's scrutiny.
Section 2. Cognitive domains. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, let's break down how your brain actually needs to process this. The Cambridge syllabus targets 3 very distinct cognitive domains here, and you need to hit all of them. First, knowledge and understanding. This is the baseline, knowing your derivative formulas and basic definitions. But honestly, that's just the price of admission. Second is application. This is where top-performing students really start to pull away from the pack. It's taking those baseline principles and applying them to entirely unfamiliar contexts, like, say, a melting cone or a leaking spherical tank. Finally, we have analysis. This requires pure logical reasoning and, crucially, referencing cross-topic connections. Principal examiner reports continually highlight that candidates who integrate their knowledge, like connecting the calculus of small increments back to binomial approximations or complex geometric properties, achieve significantly higher marks. It's all about showing the examiner a connected, conceptual understanding. I want you to think of it like the Peel framework that you probably use in your essay subjects: point, evidence, explanation, link. But we are adapting it for math. You state your point, which is your formula. You show evidence via your clear mathematical working. You explain the transition logically through your calculus steps. And finally, you link it back to the original question's real-world context.
Section 3. The 5-step methodology. Let's make this highly actionable. So, how do we practically apply this Peel-style depth in the actual exam room? We need a concrete procedural framework. Remember, the assessment prioritizes analytical depth over superficial breadth. And this brings us to the exact 5-step methodology extracted directly from the syllabus guidelines. Step 1. Identify key elements. Deconstruct the question immediately. If the prompt says a radius is increasing at 2 centimeters per second, stop right there and write down dr dt equals 2. Extract the data instantly. Step 2. Apply relevant principles. Select your analytical framework. Ask yourself, do I need the surface area of a cylinder formula right now? Step 3. Execute analysis. This is the heavy lifting. This is where you actually differentiate, use the chain rule, and, this is key, maintain flawless mathematical notation while doing it. Step 4. Verify your results. Seriously, pause and think. Does a negative rate of change actually make sense if the object in the word problem is supposed to be expanding? You have to question your own assumptions. And finally, Step 5. Present in format. Use appropriate terminology, check your significant figures, and evaluate your final line against the specific command words given in the prompt. Top students, they process every single question through this exact sequence, without fail. Now you might be wondering, why is this step-by-step working so obsessively important? Why can't I just do it in my head? Because of the method mark strategy. In Cambridge exams, your final correct answer is only worth a fraction of the total marks. Let me say that again. The final answer is just a fraction. The vast majority of your grade comes from M marks, or method marks. The examiner is literally looking for excuses to award you points for clear analytical process. If you follow those 5 steps we just discussed and clearly show your notation, like explicitly writing out that delta y is approximately equal to dy by dx times delta x, you will earn method marks even if, heaven forbid, a silly arithmetic error throws off your final calculation. Under exam pressure, 2 plus 2 might suddenly equal 5 in your brain. It happens. But clear, methodical, Peel-structured working, that is your absolute ultimate safety net. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @aceexams_IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. Section 4. Interactive Workshop. Time to spot the flaws and put all this theory into actual practice. Okay, I want you to mentally engage with this next section as if you are literally sitting at that exam desk right now. We are going to do a rapid data scan based on the classic mistakes made by our students from earlier, Alex and Sam. Look at the dynamic between cause and effect. Examiner warning number 1 states that students constantly confuse cause and effect in connected rate problems. What does that mean? Well, the cause is your independent variable changing. For example, time simply passing or a radius independently expanding because it's being heated. The effect is the dependent resulting change, so the volume increasing as a direct mathematical result of that radius changing. When you are writing your chain rule out, if you accidentally swap dx dt with dy dt, you are fundamentally confusing the cause with the effect. You must extract the core trend from the data. Ask yourself, what is actively driving the change here, and what is merely responding to it? Getting this backwards won't just lose you a point, it will completely derail the logic of your entire calculation. Think about this critically. Are you making these common exam errors in your own extended responses? I really encourage you to go evaluate your own recent past paper attempts. The syllabus specifically demands that you evaluate the quality of the evidence you're providing. Are you identifying the limitations of the mathematical models you're throwing on the page? Are you making massive unsupported assumptions? For instance, if a question asks about a small increment in a variable, are you just blindly assuming the rate of change is perfectly constant over a really large interval, when realistically it's actually not? Evaluative, high-level thinking means actively questioning these assumptions. It means considering different perspectives and, as we talked about with the Peel framework, justifying every single step of your mathematical decision with clear, undeniable notation. To wrap up this interactive scan, let's reveal the top 3 mistakes pulled directly from the principal examiner reports. Consider this your definitive cheat sheet for what not to do. Mistake 1, confusing cause and effect, which we literally just decoded. Mistake 2, forgetting to check format and presentation. Are you leaving your answer as an exact messy fraction when the specific command word strongly implies a certain number of significant figures? That's an easy mark lost right there. And mistake 3, answers not specific to the context given. This is a huge one. Let's say the question is about water actively leaking from a tank. If you leave a negative sign in your final written sentence describing the amount of water lost, you've just created a double negative that completely ignores physical reality. You can't lose a negative amount of water. Your final sentence must tie directly and logically back to the real-world physical context of the problem. That is the link part of our Math PEL framework.
Section 5, the final blueprint. Let's bring this all together.
We've defined the wasteland. We've broken down the cognitive science of exactly how examiners test you. We've built a 5-step methodology, and we've debugged the most common logical errors out there. So here is your finalized mathematics success system, your blueprint for absolute analytical depth. Rule 1. Decode the command words. Honestly, before your pen even hits the paper to write a single number, highlight what the examiner is actually asking for. Is the word evaluate? Is it show that? Or is it find an approximation? They all require vastly different approaches. Rule 2. Apply the 5-step framework flawlessly. Identify, apply, execute, verify, present. Do not skip a single step, and always remember those safety net M marks are hidden entirely in your execution phase. Rule 3. Matrix time management. You have to allocate your exam time strictly based on the marks available and the cognitive domain being tested. Please do not spend 10 minutes agonizing over a simple 2-mark knowledge question, and conversely, don't rush blindly through an 8-mark analysis synthesis question. Pace yourself intelligently. You control the clock, not the other way around. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos.
Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCE and clip that bell. Don't let another exam pass you by.
Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.